Hi, this is Sharmila Shankar here to help you understand what memory segmentation is. Let's see how the memory is segmented in 8086 and the advantages of memory segmentation in 8086. So segmentation is the process in which the main memory of the computer is divided into different segments and each segment has its own base address. We could see from the diagram that the 1 MB of memory here, which is supported by 8086 architecture, can be splitted into 16 different segments, each running for the length of 64K. So here at any given time only 4 segments could be active. So here to gain access to these 4 segments, 8086 provides 4 special registers called as segment registers. So here the 1 MB of memory is divided to 16 segments of 64K each, and 8086 allows only 4 active segments as I said earlier. So here we need only 4 base addresses to be remembered, and these 4 base addresses will be stored in 4 different registers that are supported by 8086. So physical address of 8086 is 20 bits wide to access 1 MB of memory location. But we know that the logical addresses are just 16 bits wide. But let's see how we are going to arrive at 20-bit physical address using this 16-bit registers, and how we are going to address various memory locations of this 1 MB of memory that could be accessed by 8086. So here the 4 segments which I mentioned earlier which is there in 8086 is of 16-bit length, and it is going to have the starting address of these memory segments which are active. So here a segment is a logical unit of memory that is made up of 64 kilobyte long, and each segment is made up of contiguous memory locations. So it is independent and separately addressable unit. So starting addresses will always be changing and it will not be fixed. So as we know that we can have many different segments of this 1 MB that could be accessed by 8086. So only 4 segments are going to be active. So at any given time, the starting segment address may vary. It is not going to be fixed anyway. Now let's see how the 1 MB of memory could be segmented, and it could be accessed by the 886. So here we have 2 different kinds of segmentation possible. One is overlapping segment and the other one is non-overlap segment. So if we just look into this figure, so we could see that the segment 1 here and segment 2 is overlapping. Even though it is not fully overlapping, yet actually that is segment 2 starts in the middle of segment 1. So which actually tells us that when segment 1 is active, segment 2 need not necessarily be active because there is an overlapping. So if at all this segment, that is the data that is stored in both these segments, are going to be shared, then these two can be active at any given time. So here we can have 2 different types of segmentations possible. Basically one is overlapping and the other one is non-overlapping. So looking into this diagram, we could see that segment 0, segment 1 and segment 4 are non-overlapping, whereas segment 1 and segment 2 are partially overlapped and segment 2 and segment 3 are fully overlapped. Now coming to the segment registers. So these segment registers which I mentioned earlier actually come in the bus interface unit. So here we could see in the diagram that we have 4 segment register, namely code segment register, data segment register abbreviated as DS, and stack segment register and extra segment register. So here these are used to hold the 16-bit of the starting addresses of 4 memory segments that are active at any given time. So starting addresses are also otherwise called as base addresses or segment address. So all segment registers are 16-bit wide. We could see from here in the diagram it starts from 0 and goes till 15, which means that it could accommodate maximum of 16 bits of data, or which are that is the actual address. But it is necessary to generate 20-bit address on the address bus, because we know that every memory location in the 1 MB memory could be addressed only with 20-bit address, not just 16-bit address. So here how actually we arrive at this 20-bit address with the help of the 15-bit address that is stored in the segment register is like whatever the segment register holds is the base address, is the starting address of the segment. So we're going to just rotate or just left shift the bits in this code segment or data segment register in order to either access instruction or data for 4 times, and just add the offset that is going to be there in one of the registers like instruction pointer or base pointer or the stack pointer register. So here you could see in the diagram that we have SP, which is nothing but the stack pointer register, and this BP, base pointer register, and DI, destination index, SI, source index, and IP, the instruction pointer. So here the offset that is going to be used to calculate the actual address from the effective address that is stored in the segment register are going to be there in one of these registers mentioned. So here IP is associated with code segment register, that is whenever you try to access or retrieve an instruction from the set of instructions stored in the memory, then we're going to take the IP as the offset value, that is the value that is stored in the IPS offset value, and the base address is going to be chosen from code segment register from the bus interface unit, and we do calculation in order to calculate the actual address, and then we arrive at the 20-bit address. So this is going to be shifted 4 times, and this will be added along with this base address so that we get 20-bit address. So here this 16-bit when shifted 4 times will be added with 4 zeros at the end or the LSB side, and this 16 bits will be added there. Now coming to the code segment register, this register holds the upper 16-bit of the starting address of the segment from which the bus interface unit is currently fetching the instruction code byte. So here this is 16-bit wide, and this contains, as I said, is going to have the base address of the current code segment. And the 20-bit physical address will be calculated by logically shifting the contents of CS 4 bits to the left and then adding 16-bit to the end, which is nothing but the content of the instruction pointer. Now coming to data and extra segment register. Data segment register is associated with the part of the data that is stored in the memory. So here whenever the CPU wants to gain access to the data, then it's going to take the base address from the data segment register, and the offset can either be chosen from base pointer or the index registers according to the addressing mode that is being used by the system or the programmer. And coming to the stack segment register will hold the current stack address or the stack segment address. It is going to have the base address of the stack segment, and the 20-bit physical address is calculated with the help of the stack pointer and the stack segment address. So this is used when the program has got push or pop instruction in it. Thank you.